So now that we've been playing around with exponentials and their general shape, we're now going to start looking at derivatives of those exponential functions. Now, you remember from last year when we introduced derivatives, the derivative function gives you the slope or the gradient of every single point on the original function. Now we're going to look at exponential ones. Now let me just show you something first. If I had this particular function, y equals 2 to the power of x, if I were to graph it, it's going to look something like that. Now if I drew the derivative, worked out the derivative of it, which just by the way is going to be the 2 to the x stays the same, and I multiply it by the natural log of 2. You might remember me talking about natural logs last year. They're going to come into play quite a lot now. So times them together, and then if I graph that, I'm going to get a graph that's exactly the same shape, and it's going to fall there below the original one. If I were to draw the graph of 3 to the power of x, it's going to look something like that. Its derivative is actually going to be, so again, 3 to the power of x stays the same, times it by the natural log of 3. Its derivative is going to fall exactly the same shape, but fall above the original curve. 2 to the power of x, its derivative was below the original curve. 3 to the power of x, its derivative is above the original curve. There must be some particular value, down this base down here, that when I take the derivative of it, its derivative function and the original function turn out to be exactly the same thing. And yes, that does exist. It's called e. Y is equal to e to the power of x. E is one of those numbers just like pi. It's transcendental. It goes on forever. It doesn't repeat. It's very useful in our exponentials, and we're going to use it all the time from now on. So e's approximate value is 718281828 2, 3, 5, 4, 5, 9, 0, 4, 5, and on it goes forever. So that's its approximate value. So instead of writing that messy, horrible, ugly number, we just write e. Now, functions that are exponential functions with a base of e have this incredible property. Now, the only functions that do it is that functions that are exponential with base e, the derivative is another exponential with base e. It doesn't change. That is the only function you're ever going to come across where its derivative is itself. Now I'm going to give you just one example of that. So let's have a look. If I gave you y is equal to x squared e to the x, and we had to find the derivative function of that. Now, please note, what sort of scenario do we have here? Remember, last year we came across a number of situations. We came across chain rule, product rule, quotient rule. This is an example of the product rule, where you have one function being multiplied by a second function. Now, to do that, we need to split it into its two functions. U squared, where its derivative is 2x, and then v is equal to e to the x, and so we've just learnt e to the x is a derivative, gives it to e to the x. Now, so let's now start applying product rule as we used to. So product rule is, it's going to be the first multiplied by the derivative of the second, plus the second multiplied by derivative of the first. That gives me x, that was silly, x squared times e to the x plus e to the x times by 2x. Now, we can, common term of e to the x, we can factorise that out. If you wanted to, you could factorise a bit further and take the x out, x e to the x outside of x plus 2. But that's an example of doing derivative with exponentials. Now, before I get too much further into any more videos, I'm going to put one more example up on the board that you need to know about. So just give me a moment to get that set up. Now let's have a look at this situation. Y equals e to the power of 3x. Previous example was a product rule, two functions times together. I've now got an example of a chain rule. I've got an inside function, which is 3 to the power of x, and an outside function, e to the power of whatever the inside function is. So, break it down as we normally would. Y is equal to e to the power of u, where u is equal to 3x. And we'll just do a fully worked chain rule from here. dy du, well, we know that e differentiates to give itself, so e to the u differentiates to give e to the u. Nothing's going to change. Du dx will be 3. So the differential of the original function in terms of x will be dy du times du dx, excuse me, e to the u times by 3. So that's 3 lots of e to the power of, take u out, put its value back in. There's our derivative. So let's have a note. You should be able to, by inspection, go from the question to the answer in one step. On the exam, I'm going to expect you to do at least one fully worked chain rule to show this, but I'd like you to be able to look at that and go to that in one step. And what do you notice? E to the 3x stays as e to the 3x. And what do I multiply out the front by? Derivative of the chain. The derivative of 3x is 3, so at the front it goes. So they're the two types of problems you're going to come across. You'll come across quotient rule ones as well, but you're still applying the same idea, that e derives to give itself, and that's the principle that we're working under. So good luck with derivatives of exponential functions.